Here, I'm going to do a presentation that is a bit atypical because I'm not an expert on the history of mathematics. But for reasons that I don't have time to go into, maybe 10 years ago, I read Gauss's original memoir on what's now called Gaussian quadrature. And I was quite surprised to see that what's in that memoir is very, very different from the presentations on Gaussian quadrature that you read in textbooks that I later learned go back to Jacobi. So this memoir was read at the Academy in 1814. It's a new method to find the values of integrals by approximation. And the rules of the presentation is that whatever in the slides is in the original memoir will be written in black or blue, and I've written in red my own comments and so on. For the blue part, I've kept Gauss's notation because I think that's of some interest. So this booklet contains 40 pages and 23 articles, and the first pages are just a review of the formulas by Gauss on quadrature with uniformly spaced nodes. So the first contribution of Gauss, which is not in quotes, starts at page 11, where he shows how to construct quadrature formulas when the nodes are not uniformly spaced. So I've kept some of the Latin here. I hope you can understand this. So the problem is to compute this integral between given limits when different values of y are known. And the integral have to be computed from x equals to g to x equals to g plus delta. And he first performs a change of variables, goes from the original variable x to an auxiliary variable t that runs from 0 to 1 by this change of variables. And the data is that we are given n+1 values of y and the corresponding values of t, that are those small letters. So Gauss starts by writing what we would now call the Lagrangian interpolating polynomial, and then he proceeds to compute the integral of the interpolant. But before he does that, he rewrites the numerators and the denominators in this expression as follows. So he introduces this t that is very important in what follows. For you to remember, this is written on the blackboard. So t is the polynomial of degree n+1, whose monic polynomial, whose roots are the abscissa, and he denotes the roots are alpha, are a's, the abscissa, and the coefficients he denotes by alpha, alpha prime, alpha prime, and so on, and so forth. And having introduced this t, of course, we see now that the numerators are just the result of dividing this polynomial t by t minus a, t minus a prime, and so on. And then, of course, the factors in the denominator, m prime, are the values of the numerator at the abscissa. So with this polynomial t, the interpolating polynomial becomes like this. And then the next step is to find explicitly the value of m here, and then to integrate the functions t divided by t minus a and so forth. So how does he compute m in terms of the coefficients of t and the abscissas? Well, he writes t as given here, so he uses that t vanishes at a. So this is t at t minus t at a. And then he divides by t minus 1. So this is quite an awful, not a very nice computation. And then he evaluates this t, this expression at a, and then he concludes that the factors in the denominator are the values of the derivative of capital T with respect to t evaluated at the abscissa. Well, I'm sure that all of you could compute that this is the value of the derivative in 2 or 3 different ways that are much easier to what Gauss does, but just in case we thought that we were more clever than Gauss, he writes that this is obvious in other ways. So he was aware that he could have done this in a much easier way. And the reason he does this is that because then he uses this, the expression, to compute the integral. So he now integrates. So this is the value of the integral, not very nice. And then after this, he rearranges. So he writes sums by columns. And then this is the expression that he gets for the integral of t divided by t minus a. And now, just to show you how clever he was, once he writes this, that to me looks complicated, he says that this is not complicated because this obviously is the result of multiplying our polynomial t by this rational function. And once you've multiplied t by the rational function, you discard the terms with the negative powers of t and then replace t by a. So this is the result of the integral. I mean, really complicated to me. So to be more precise, he writes this formula that for your benefit I've copied there on the blackboard. So he multiplies t by this strange rational function. The result, because this starts with t to the n plus 1, is a polynomial of degree n. And then, so this is a polynomial, and this contains the negative powers of t. So please remember that formula that for your convenience is written there on the blackboard. And remember that prime and double prime don't refer to derivatives because he uses Leibniz notation for the derivatives. And then the previous discussion says that the integral, this integral that he needs to compute is just the value of that this polynomial of degree n takes at t divided by a. So he puts everything together, and then the quadrature formula is like this. The capital A's are the given ordinates for the quadrature, and the R's are the weights. And then the weights are just the value of the polynomial t prime divided by the polynomial dt evaluated at the abscissas. So once he's found this general expression for the quadrature, then he repeats everything, but not in terms of this auxiliary variable t that runs between 0 and 1, but in terms of an auxiliary variable u that runs minus u and minus 1 and 1. This he does to later to be able to exploit the symmetry. And then when he does this, the abscissas are b's, and then the polynomial t has to be replaced by this polynomial capital U. So he repeats everything, and then as an example, Gauss finds explicitly the weights for the Newton-Cotes formulas, both in terms of the variable t and the variable in the variable u. And then, having found the formula, he goes into the error analysis. So he denotes when the function to be whose integral has to be computed is t to the power of m. He denotes the quadrature error at k superindex m. So this is the quadrature value, this is the true value of the integral, and this is the error. And then he multiplies across by t to n minus 1, and then he gets this identity between functions. So this is this strange function that has appeared before, this rational function. This theta is a rational function whose coefficients are the errors, and this is the rational function associated with the quadrature. And you note that because of the construction, the formula is exact when you, for the functions 1, t squared, up to t to the n, and therefore k prime up to k superindex n must vanish. This is what he says. And this slide is very important because even though Gauss doesn't explain anything, he just shows things, trying to impress you that he's very clever, but he never explains his reasons or his arguments. This formula is really the most important thing in the memoir, because so what he does is he goes from sequences of numbers, say km, this is the quadrature error, and then he makes this what we could call a Z transform or a generating function. He goes to a rational function whose coefficients are the sequence that he has to work out. And then you see this is the sequence, this is the generating function for the error, this is the generating function for the quadrature, and this strange function that he came up with before without any explanation, now you realize that is the generating function of the true values of the integral, so the moments of the Lebesgue measure. So when you integrate 1, you get 1, you integrate t, you get 1 over 2, 1 over 3, 1 and 1 over 4. So you see, in a way, you could have explained things a bit better, because this is just the generating function of the moments. But and now we recall that this fourth line in the on the blackboard, that we multiply t by this fancy rational function to get a polynomial t prime and a remainder t double prime. And then in the previous slides, he multiplies across by t. Okay, so he gets t, the generating function of the quadrature, the polynomial, the remainder, the generating function of the error. But then he notes that the left-hand side is what he calls an integral function, we would say a polynomial of degree n, whose values at a prime, as he had computed before, are m times the weights. But those are precisely the values of t prime. So this has to coincide with t prime, and as a consequence, what's left when removing the polynomial, this t w prime, has to be equal to t theta. So this is important because we now can compute this theta, which means we can compute the error coefficients by simply when we know t double prime and t. And now it comes the main ideas. He points out that for any choice of the abscissa, the construction he has carried out is exact for polynomials of degree less than or equal n, but as shown by his previous example of Coates' formulas, when you have a symmetry, for some particular choices of the ingredients, the degree could be higher. So he now tries to annihilate additional coefficients, error coefficients. So in a nutshell, this theta that generates the error coefficients, we know that equals t double prime t, and this is the famous rational function minus t prime t. So for him, everything, but he doesn't explain, everything becomes a problem, a matter of approximating this function, this function, this meromorphic function or whatever, by a rational function, in the sense that they have a high contact at infinity. So everything has become a problem in what we now would call a Padé approximation. So he multiplies across by t to have a linear problem, as we would do today. And then he notes that we have n+1 free coefficients that are the coefficients in our polynomial t. So we can use those n+1 free coefficients to annihilate n+1 leading coefficients of t double prime, and then the maximum degree achievable is 2n+1. He doesn't care doesn't analyze whether the problem has a unique solution, or the abscissa are in the interval, or the weights are positive. This is not for him. And then once he's solved this problem, he repeats everything, but in terms of the variable u that ranges from -1 to 1. Then it's a matter of approximating this meromorphic function at infinity by a quotient u prime equals u. Then he works out many examples. It starts with n equals 0. So there's only one coefficient, one t. So he multiplies this t by the famous meromorphic function. He annihilates the power of 1 over t, and then he gets alpha minus a half. So you have to put the node at the midpoint. So it's the midpoint rule that uses one evaluation, but is exact for straight lines. And he does this again for 2 nodes and 3 nodes by solving the linear system and in detail. And then he repeats everything in terms of u. And then he writes a sentence that I like. He said, but this way that will bring computations that become more and more obnoxious. We will not proceed further with them, because we are not going to advance to the source of the genuine solution. I think this is quite a nice sentence, right? So from pages 26 to 36, he now does better than solving the linear system of equations to find the coefficients of the polynomial. And then I think this is very appropriate for this meeting. He has like a remainder of continued fractions. So okay, so he has this continued fractions, and he shows that if you introduce these quantities v and w, and you compute them recursively in this way, well, please note that we now are working in terms of a 3-term recursion. So we are coming closer to the Legendre polynomials. The Legendre polynomials will eventually appear here. So once you've computed those v, then the quotients of the v's, of course, give us the convergence of the continued fractions. And then he shows how to go from the continued fraction to a series, and from a series to a continued fraction. So I think this is very well known today, and we would explain it in the same manner. So just to get a reminder, if you work with this variable u that goes symmetric from -1 to 1, the problem is that you've got this function. You look at the function when u approaches infinity, and then you have to approximate this function as good as possible by a quotient u prime divided by u. So it's a problem in Padé approximation. So now he quotes himself. He quotes his memoir of 1812, where he introduced the hypergeometric series, and lo and behold, in Formula 33, in that memoir, he had written this discontinued fraction, and miraculously, this continued fraction, when turned into a series in negative powers of u, is nothing that, oh, sorry, I'm very bad at this. So here he showed how to transform this continued fraction into this series and vice versa. So we have to approximate this series at infinity, but of course, having written it in terms of a continued fraction, you just have to truncate, and the convergence will be optimal approximations at infinity. So this is what he does, and then he computes the V's and W's. He notes that in the denominators, the W's get this expression where we now recognize the harmonic Legendre polynomials, and the V's are the associate polynomials of the three-term recursions. So after this, he writes this as a series, and then he shows that, of course, if you truncate after m terms, then the convergent is the Padé approximation to phi of degree m minus 1 minus m, and therefore, if you choose your u, the function whose roots are the abscissas you are looking for, as this Wn plus 1, this means the Legendre polynomials that he has computed by the three-term recursions, this u phi will be free of those powers, and then he concludes that the abscissas have to be chosen as the roots of the equations Wn plus 1, so the zeros of the Legendre polynomial. And having said that, then Gauss provides closed form expressions for the monic Legendre polynomials of arbitrary degrees. He discusses how to write the Legendre polynomials in different ways in terms of hypergeometric functions. Then he repeats the whole analysis with the variable t replacing the variable u, and then he gives explicit expressions for the polynomial that yields the weights. And now the last 4 or 5 pages are what really a numerically inclined person likes better in this memoir. Sorry. So having presented the theory, he goes, considers the cases from n equals 0 to n equals 6, so from 1 to 7 nodes, and then he gives tabulations of the polynomials u, u prime, t, and t prime, the abscissas a prime with 16 significant digits. That must have been very time-consuming in his time. I presented this talk in Oxford years ago, and then Nick Trefethen was curious to know whether the values of the abscissas were correct. And then he plugged this into this Chep-Fun thing that he has, and then he found that most of the abscissas are correct to the number of digits displayed, and maybe in 1 or 2 there's an error in the 15th or 16th digit. So this is then he finds the weights R prime with 16 significant digits, and also when the weights are irrational and more complicated, he gives the logarithms because in those cases, of course, you have to multiply the weights by the function values by using tables of logarithms. So he also tabulates the polynomial that gives the weights, and then he gives the leading coefficient of the expansion error. So he finishes rather well. And then, as any self-respecting numerical analyst would do today, he concludes his paper by computing, by applying his method and showing that it's better than those that were available in the literature at the time. So he is interested in this integral between 100,000 and 200,000. So the length of the integral is very long, but of course the function hardly changes. It has very small derivatives. And then he informs us that Bessel had computed this integral to be to have this expression, and then he computes with 1 node, 2 nodes, 3 nodes, and to 7 nodes. And I've written in blue the digits that are kept fixed as you advance. So one sees very quickly that there's this very fast convergence, and then you have really 1, 2, 3, 4, 5, 7 decimal places that are correct by using the highest. Of course, this integral must have been of interest to Gauss in connection with the prime number theorem. So I think this is the reason he was interested in this particular. So I checked, and the number of primes in the interval is 8,392. The integral is 8,406. So I suppose Gauss was encouraged that the density of prime numbers is the reciprocal of the logarithm. How am I doing for time?
Oh, as much as you need.
Okay. Oh, thank you. This is so I haven't had time to present many comments, but since the chairman has allowed me maybe an extra couple of minutes, as a person that has been brought up in numerical analysis and computations, I found this quite remarkable because nowadays Gauss, when compared with Euler or Newton, is presented to us like a paradigm of the Princeps Mathematicorum, the ne plus ultra of rigor, and so pure mathematicians like him a lot, and so maybe those don't have such a high regard for computational mathematics. But you see, if you look at this without passion, that it was the other way around. You see how many things were weak in this memory from the point of view of rigor. For instance, he doesn't know how to deal with the error in the approximation, the polynomial approximation. He assumes that the functions are analytic without concern about any convergence or anything. When he writes the linear system of equations for the coefficients of t, he says, okay, I've got n plus 1 unknowns, therefore it will have a unique solution. He doesn't care to show that the weights are positive. He doesn't care, he doesn't realize that the abscissas are in the interval. He takes all those things for granted. The same. But simultaneously, you see that the 4 or 5 final pages will certainly be approved by any numerical analyst nowadays. He has the tables to facilitate the computations with the logarithms. He's computed everything to very many decimal places. He has a numerical example. The numerical example is relevant. He compares his approach with others that were available literature. So I would rather be inclined to think that if by some incredible amount of imagination I would be a teacher and Gauss would be my student, if this was a numerical analysis exam, I would give him full marks. But as a pure mathematician, I think maybe he's only 60% or 65 or 65 or 65%. So if any of you is interested in this and can read Spanish, this has been published in Spanish in the Journal of the Spanish Mathematical Society, whose president is the next speaker. So thank you very much for your attention.